two basic types of bearings are used: friction and anti-friction bearings. Friction bearings have a sliding contact between a shaft and the bearing. A special, low-friction material lines a rigid housing. The lining directly contacts and supports the shaft. In use, the shaft slides over the liner material, separated by a thin film of lubricant. The area of contact is relatively large, and pressure on the bearing material is usually low. Friction bearings are also referred to as plain bearings, sleeve bearings, and journal bearings. The journal is the part of a machine's shaft that is inside the housing of a bearing. Anti-friction bearings have a rolling contact between the shaft and bearing using balls, needles, or rollers. In this type, the area of contact is very small and the pressure on the rings and balls or rollers is quite high. The housing, sometimes called a pillow block, of a bearing is its outer casing. The principal parts of the housing of a friction bearing are the base bolt slots, the cap, and the cap bolt holes. Housings are made of one of the following materials: cast iron for general use with light to medium loads. Cast steel for general use. It is stronger than cast iron and can be used for light to heavy loads. Fabricated steel for bearing housings for special jobs. The choice of a bearing housing depends on the load, the rotational, or rubbing, speed, the direction of pull, and the support design. Dimensions of friction bearings. The bearing has a nominal size such as 2/7116 bearing. This is the size of the bore of the bearing, ID in Figure 3. Note this is not called a 2.4375-inch bearing. Other dimensions are also fractional, not decimal. The dimension from the base to the shaft center, called the eye of the bearing, is important for installation and alignment. Bearings of the same size, design, and service weight from the same supplier have the same shaft center dimension. Bearings from different suppliers may have different values for this and other dimensions. Styles of friction bearings. The choice of a bearing depends on the load, the rotational, or rubbing, speed, the direction of pull, and the support design. Regular or flat bearings. The two kinds of flat bearings differ in their housings. They are solid bearings and split bearings. Solid bearings. Solid bearings are used when speed and load are low. They are designed to be used in locations where the load is applied to the top part of the bearing. Solid bearings are frequently mounted in an inverted position. They must be slid on or off the shaft, which means that the bearings must be put on as an assembled unit. Split bearings. Split bearing designs vary from one manufacturer to another. A 2-bolt bearing is used for light to medium loads. A 4-bolt bearing is used for medium to heavy loads. Angle bearings. Angle bearings are used for drives in either of the following situations: when the load is applied parallel to, or at a slight angle to, the horizontal. When the bearing is mounted on a vertical support. Integrated bearings. Some heavy-duty machines and industrial plants have the bearing base cast as an integral part of the machine. These bearings are either babbitt or fitted with shells or liners like other journal bearings. Joint design. You must consider the design of the bearing joint when choosing a bearing for a specific job. Bearing joints are designed in 3 general styles: with flat joints, with a gib in the joint, with an angle joint. Flat joints. When the joints are flat as shown in Figures 5 and 6, the bolts hold the cap in alignment. The opposite sections of the joint may be completely level with each other, called flat joint bearings, or be at an angle, called flat joint angle bearings, as shown in Figure 7. Jib joints. When the joints have a little step in them as shown in Figure 8, they keep the cap from moving sideways. A gib bearing combines the rigidity of a solid block with the advantages of split construction and is suitable for limited side loading. If the bearing has gib joints, it need not be loaded only on its bottom half. Liner materials. Journal bearings and pillow block bearings with anti-friction material liners are commonly used for low to medium speed and for light to heavy loads. They can be used for ultra-high speeds with air-jet lubrication only under exact conditions, for example the main bearings on a turbine. When selecting liner material, it should be softer than the shaft material, so it deforms slightly under heavy loads. Of low coefficient of friction, wear resistant, a good heat conductor, and remain relatively stable with heat changes. Readily available. Metallic liner materials. Metallic bearing materials must have a low coefficient of expansion. They are also dimensionally stable in the presence of water. They may react chemically with water, mild acids, alkalis, salts, or other materials. 9.5. Metallic liner materials are Babbitt for general use, brass, copper/zinc alloy, for higher speeds and heavier loading than Babbitt, bronze, copper/tin alloy, for higher speeds and heavier loading than Babbitt, aluminum, common in hydraulic pumps, sintered bronze, used for self-lubricating chain. This is a porous bronze with a built-in oil supply oilite. Oil-to-bronze ratio is 1:2 by volume. Non-metallic liner materials. Non-metallic liner materials are nylon, polyurethanes, phenol laminates such as Celeron-TM and micarta, nylons and polyurethanes. Nylons, polyurethanes, and other synthetic bearing materials are sometimes called plastic bearing materials. The advantage of plastic bearings is that they are generally inert to most mild acids and alkalis. The lubricant for nylon or plastic bearings can be oil or grease, but water is also used. With low rubbing speeds and low operating temperatures, some grades of nylon will run with no lubrication. They have varying coefficients of heat expansion, all higher than those of metallic bearing materials. In addition, some synthetic materials expand when saturated with water. Before doing any critical fitting, check the specifications of the material. Basic nylon has a thermal expansion rate roughly 10 times that of steel and a fully saturated water expansion rate of 0.0256 inch per inch of material. Heat expansion is fairly constant through the grades. This is important when dry fitting a nylon bearing which will run with water lubrication. Phenol laminates. Phenol laminates have layers of cotton or other natural fillers bonded with phenolic resin. They are strong, shock-resistant, and compatible with most fluids. Babbitt. Babbitt is a common anti-friction lining material for bearings. It melts at a temperature of about 288 degrees Celsius, 550 degrees Fahrenheit, or less. In a liquid state, it fills all cracks, voids, and irregularities in a casting, giving a smooth surface to match the shaft surface. Babbitt can be used in badly worn bearing housings, thus eliminating the cost of a new housing. Figure 9 opposite shows a Babbitt lining in a new and a worn bearing. Babbitt includes several alloys that contain various proportions of tin, copper, antimony, and lead. Tin-based Babbitts, copper or antimony with up to 90% tin, are the hardest and the toughest. Tin-based Babbitt with a very high tin content is sometimes called nickel Babbitt. It is used in conditions of heavy service and extreme pressures. The introduction of a small percentage of lead to a tin-based Babbitt gives a slightly softer material. Lead-based Babbitts are those in which the tin has been largely replaced by lead, up to 10% tin and 75% lead. They are cheaper and can be used for light loads at low speeds. When pouring Babbitts, the 3 temperatures to consider are complete melting point from 275 to 285 degrees Celsius, 495 to 545 degrees Fahrenheit. Pour point from 343 to 371 OC, 650 to 700 degrees Fahrenheit. Complete solidification point from 25 to 28 degrees Celsius, 40 to 50 degrees Fahrenheit, below the complete melting point. Do not overheat the Babbitt. If Babbitt is overheated, the service life of the material is greatly reduced. Overheating Babbitt is equivalent to overheating an anti-friction bearing to install it on a shaft. The physical shape is not altered, but the normal service life is reduced. Keys. Babbitt is held in position in a bearing casting by keys, which are grooves or slots in the casting. Any bearing liner to be re-Babbitt must have the keys cleaned out. Figure 10 on the next page shows Babbitt holes and slots. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Holes. Figure 10 Babbitt holes and slots. Using mandrels to pour Babbitt. A mandrel, dummy shaft, is used to shape and size bearings. It is a short, smooth piece of shaft to the required diameter and several inches longer than the widest bearing to be poured. When a lot of Babbitting is being done, the most common sizes of mandrels are fitted with side pieces to help positioning. Mandrels come in the following styles. Plain mandrel. Mandrel with side pieces. This can be quickly centered in the bearing. When the bearing base is set up and the mandrel is in position, The poured babbitt is held in place by a ring held in position with a backing of babbitt putty, a commercial product manufactured specially for this job. Pouring babbitt. Pouring babbitt can be quite dangerous and is usually done by a designated millwright in the plant. Always observe the following safety measures when babbitting. When you pour into a bearing and mandrel assembly, make sure that it has been heated to 94 degrees Celsius, about 200 degrees Fahrenheit. First, to remove any free water or surface moisture. Free water causes a blowback or explosion. Use all protective equipment as called for by Workers' Compensation Board, WCB, rules and regulations. Company safety policy. Preparation for babbitting is critical. The shaft must be brought up to level or aligned to other parts of the machine. Since you cannot adjust the position of the bearing, the vertical and horizontal shaft positions are most important. Emergency pouring. A situation sometimes arises when a bearing bums out and has to be poured in a rush in order to let the operation run to the end of a shift. The following procedure for emergency pouring is effective for temporary work on bearings with low-speed shafts. Keep a fire extinguisher handy, as the oil on the outside of the bearing will often catch fire from the torch. 1. Gather the following equipment: fire extinguisher, oxyacetylene torch, putty, pair of pliers, cake of babbitt. 2. Fit the torch with a large tip and melt out the remaining babbitt in the casting. 3. Smoke the shaft with a straight acetylene flame. 4. Put a putty dam around the shaft and bearing. 5. Hold the babbitt with the pair of pliers. 6. Melt it into the bearing with the torch. Tinning babbitt bearings. When a thin skin of babbitt must be firmly attached to a metallic backing, a tinning process is used. The process is similar to that used in brazing a brass coating. It requires a heat source, such as an oxyacetylene or propane torch. Fitting a babbitt bearing for contact. As the babbitt is poured, it fits perfectly to the shaft and allows no clearance for lubricant. Any bearing, regardless of shape or friction material, must be prepared carefully. You must check surface finish and area of contact, running clearance, a lubrication entry for setting up the oil wedge, grooves for distributing the lubricant, hand tools for fitting bearings. Hand tools, such as scrapers, used for fitting bearings may be commercially produced or made in the plant to suit the millwright's preference. Figure 13 shows some babbitt finishing tools. Scraper cutting surfaces are curved or straight. Curved scrapers are usually commercially manufactured and tend to produce a wavy finish. Straight scrapers are usually homemade and produce a flat finish. Homemade scrapers with smooth, sharp edges can be made from various kinds of files: mill bastard, half-round machinists, or triangular ground files. They should be ground slowly and carefully to prevent burning or local hot spots that will change the temper of the steel. The fitting process. 1. After the bearing has been babbitt, the comers of the bottom half of the bearing must be relieved to keep the shaft from binding. This is shown in Figure 14. Figure 14 bearings with relieved corners, exaggerated for illustration. 2. The top edge of the bearing must be chamfered almost to the comers as shown in Figure 15. This channels the lubricant to the shaft. The amount of chamfer is usually up to the individual, but the chamfer is often greater. 4. Grease lubrication. Then for oil. For heavy loads, the bottom part of the bearing is chamfered also. Chamfer for oil. 1. Do not cut to end. Bearing yen F. End. Figure 15 bearing with chamfered corners. To obtain a better lubricant entry, the chamfer can be extended on the entry side, almost down to the area of contact between the shaft and bearing material. 3. Another alternative is to cut an oil groove in the center of the bearing to help maintain an effective oil wedge. This method is used mainly for casual, marginal lubrication. See Figure 16. Figure 16 chamfering and grooving a bearing. Always cut grooves in the unloaded section. Do not extend grooving or chamfering into the load area or the high-pressure film area of the bearing. Usually, regardless of the load put on a split bearing, the groove is cut in the center of the bearing cap. Sometimes, the groove must be specially located to accommodate unusual loads. The bearing in Figure 17 has a load applied horizontally to the side of the bearing. It is shown with the oil supply and groove in the recommended location. Figure 17 special grooving for horizontal loading. A one-piece or solid bearing used in an inverted position may need to be lubricated through the base of the bearing rather than through the bearing cap. The grooving is in the unloaded section. 4. After the chamfers and or oil grooves have been cut in the load-bearing surfaces, check the bearing for contact. To do this, lightly coat a mandrel or shaft with mechanics bluing and rotate it in the bearing. For a good impression, apply the bluing in a light, smooth, even coat. The bluing wipes off at the points of contact and transfers to the bearing surface to show the high spots. Do not use layout INK. An untouched bearing has high points along the edge. Remove these by scraping to allow the shaft to make contact with the bottom of the liner. Figure 18 shows contact points on bearings at various stages. 0, 0, 0, 0 equals 0, 0. Figure 18 fitting bearing for contact. Clearance in a bearing. When a bearing is assembled, there must be a small amount of clearance between the shaft and the bearing cap. This prevents a binding or clamping action on the shaft. To adjust clearance: 1. Put between the bearing has the original shim used for babbiting the cap, or a shim of the same thickness, and an additional thin shim. 2. Make sure that the shims do not touch the shaft. Shape them to clear the chamfer cut in the babbitt. 3. Tightly bolt together the cap and base, and then try to rotate the shaft or mandrel. 4. If the shaft does not rotate, for a Gibb-style pillow block, add more shims. For a flat split bearing, pull the cap slightly to one side by the cap bolts, and align the cap with a few sharp blows with a ball-peen hammer. If this does not work, add more shims until the shaft turns freely. Shims. Shims are made from material that will not compress and is not affected by oil. For example, they can be sheet packing, tin plate, or brass shim stock. Slip-in shims are used in Gibb-style blocks or any split block. This type of slip-in shim may be lost if the bearing cap becomes loose. The advantage of a slip-in shim is that it can be inserted or pulled out after slacking off the bearing cap. Shims made to fit over the cap bolts will not get lost, but the bearing cap must be taken off to adjust the amount of shim, as shown in Figure 20 on the next page. Millwright, GA, RLNGs, J. Shaft. Shim for 2-bolt bearing, shim for 4-bolt bearing. J. Shaft, shaft, shaft J. Narrow shim style bearing. Figure 20 shim styles. Amount of clearance. The amount of clearance set into a friction bearing depends on machine design and company policy. Some machines with a constant load toward the base of the bearing do not have a fitted cap. The cap merely keeps out foreign material and supplies the lubricant. As a general rule, for any shaft/bearing assembly, with constant one-direction load and rotation, bearing clearance can be from medium to loose. With reversing rotation and fluctuating load, bearing clearance can be from medium to tight, see Table 1. With reciprocating action, the clearance must be tight, see Table 1. When fitting small bearings in the shop, clearance is often determined by working a feeler gauge between the shaft and the shimmed cap. In large bearings that have been poured into place, it may be impossible to turn the shaft, and steps must be taken to check the clearance under the cap. For some, the cap must be removed; for others it is not necessary. If the bearing is open at either end, you can insert long pieces of feeler stock of varying thickness to check for clearance under the cap. If the bearing is shielded at both ends by gears or pulleys, the simplest way to check is to 1. Mount a dial indicator. 2. Pry or jack up the shaft in small increments while watching the reading on the dial. See Figure 21. To check clearance by reading the dial. 1. Mount jacks at both ends of the shaft to lift the shaft evenly for an accurate reading. If a jack is mounted at only one end of the shaft will tilt in the bearing and give a false reading. 2. Note that the dial indicator reading gives the total clearance in a bearing. It does not indicate the high and low spots. Check the wear by visual inspection. To check clearance without an indicator dial, using plastic gauge. 1. Choose plastic gauge stock, called plastic gauge, with diameter about equal to the clearance. Use common sense in choosing the diameter. If the expected clearance is in the 0.010 inch to 0.015 range, pick a diameter slightly larger than this. For some bearings, you can use lead wire such as 50/50 solder rather than plastic gauge stock. 2. Take off the bearing cap and place lengths of the plastic gauge across the shaft in several places. They should reach from one edge of the base to the other. Number each piece of plastigage on the shaft. Continued. 3. Have a record sheet handy, with space to record all readings. 4. Check that the plastigage is not pinched at the comers of the top cap of the bearing. 5. Tighten down the cap, then take the cap off carefully because some plastigage pieces may stick to it. 6. Compare the width of the crushed plastigage with the chart on the side of the packet. To check clearance using lead wire. 1 to 5. Use the same procedure as for plastigage. 6. Measure the thickness of a wire with a micrometer. Start from the same end of each wire and take the wires in sequence. 7. Record the thickness of each compressed wire. This process takes time and may have to be repeated several times. The routine should give an accurate readings of the high and low spots in the bearing. The routine can also be used to check a worn bearing for excessive clearance. R. Lead wires flattens under pressure. 0. Figure 22 wire check for bearing clearance. Figure 23 represents a new bearing installation with a chamfer cut to allow oil to reach the point of contact. Figure 23b represents a worn bearing with a small, inadequate chamfer and too much bearing contact. You can scrape the worn bearing to improve the lubricant entry and surface finish. For proper fitting, the bearing B should be scraped until it resembles bearing A. AB. Figure 23 bearing wear. Preformed bearing liners. Shells. Shells are two-piece liners installed in a bearing housing. They are usually held in position by pins or dowels, screws, special bearing designs, compression, or combinations of these. They are made from any common metallic or non-metallic bearing material. Fitting shells for surface finish, lubrication entry, clearance and lubrication is done by the same procedures as for poured bearings. Figure 24 shell crush clearance. When shells are first installed, they frequently extend past the face of the bearing by a small amount, which is known as the crush, or the crush allowance. This is shown in Figure 24. When the cap and other shell half is installed and the fasteners are torqued to the correct tension, the shells are forced into full contact with the housing. If the shells are machined for the bearing, the crush allowance should not be changed. Shells can be installed and used in two cases. Where there is no adjustment for wear, that is, when shells are worn a certain amount, they are replaced. Compressor connecting rods are a good example. Where adjustment for wear is obtained by shims between the cap and the base. To obtain effective crush or clamping action, the shims must be between the shell halves as well as between the cap and base. One advantage of shell liners is that, in some machine designs, the worn liner may be removed by taking the weight of the shaft off the liner by removing the cap and rolling out the worn liner. Hold base liner against shaft. Rotate liner and remove. Roll a new liner in same manner. Figure 26 rolling out a worn shell liner. Bushings. Bushings are one-piece liners and can be made from any of the common bearing materials. Fit and clearance is usually set by the dimensions machined into the housing and bushing. It is held in position by a press fit and dowels, or by dowels with the clamping action between cap and the base. Small bushings can be reamed to bring the bore to the correct diameter. Large diameter bushings often require honing or scraping. If the bushing is supplied with an oil hole, you must align the oil hole with the supply line when pressing in a bushing. With some bushings, the oil hole may be drilled after installation and should therefore be scraped to remove any high spots caused by the drill pushing through the surface. When the bushing is worn, it must be replaced, as there is no adjustment for clearance on a bushing. Figure 27. Thrust control. Friction, plane. Bearings are usually considered radial load bearings with limited thrust capacity. Thrust, axial force, is mainly controlled by the use of other components. The thrust in a plane bearing is controlled by a shaft collar fastened on the shaft, or by a thrust washer backed by a sprocket or any other hub. See Figure 28. Such a design is good for low speeds, light to medium intermittent thrust loading, and simple lubrication. Figure 28 thrust control in a plane bearing. Thrust of a shaft is controlled by the shaft shoulder, see Figure 29, and a collar that adjusts the amount of end float. End float is the amount the shaft moves axially in a bearing. It is also called end play, axial float, or axial displacement. The shaft shoulder may not be high enough to provide enough area of contact. If this is the case, you may add a collar array, machined component in contact with the bearing surface. This style of thrust control is good for high-speed applications. Figure 29, end thrust in a shell bearing. The liner material that covers the ends of the bearings can be any of the following. Solid babbitt poured in the bearing. Shells made of brass or bronze. Brass shell with a tin-quality babbitt wear face. Some bearings are designed to carry both radial and thrust forces without the use of other components. The shaft has a number of parallel grooves which match grooves in the liner material. Liner material can either be babbitt cast in place in the housing or shell liners that have been machined to suit the shaft profile. There is no adjustment for end thrust control, and lubrication can be a problem. Kingsbury thrust bearings. The Kingsbury bearing is a special thrust bearing designed to take high speeds and heavy loads. It comes in a variety of styles. The basic design consists of a revolving ring with a flat contact surface, usually hardened and ground. A stationary ring with a number of flat contact surfaces of a low-friction material, either brass, bronze, or a tinned-on, high-capacity babbitt on a brass backing. These surfaces are separated by lubricant grooves and have chamfers or slopes on the leading edges to set up oil wedges. In Figure 30, there are 6 contact surfaces. In the bearing shown, oil flows from the center of the ring to the outside due to the centrifugal force of the bushing ring throwing oil outward. Lubricant must be supplied to the center of the bearing. Kingsbury bearings come in the following styles. Fixed pad A backing, which has a convex shape and fits into a mating housing to correct for minor misalignment. Figure 30 shows this type of Kingsbury bearing. Floating or tilting pad individual load blocks are pivoted on the fixed ring to adjust for thrust and load as shown in Figure 31. Guide bearings. A guide bearing is used as a positioning device or guide for linear motion. It is used for such things as machine tools and gas compressors. It often has a thin layer of bearing material on its surface to reduce friction, but normally operates with lubrication. Figure 32 shows one example of a guide bearing. Pivoted shoe bearings. The pivoted shoe bearing is a split journal bearing used mostly for high peripheral speeds and shaft stabilization. The shoes are machined cylindrically to fit freely in grooves in a retaining ring. See Figure 33. Its operation is like a flat, tilting pad, Kingsbury bearing. The surfaces of the shoes and rings are corrosion-resistant and low friction. The bearing is doweled so that the upper and lower halves can be joined in only one way. The lower half of the aligning ring also has a dowel to position the bearing axially and prevent rotation. Each shoe has a separate oil inlet, which helps to lower the operating temperature and keep it uniform. The plates are bored so that spent oil discharged from the bearing is regulated without shaft contact. When using and maintaining pivoted shoe bearings, carefully inspect the babbitt surfaces, pivoting surface and seat, and the diametral clearance between shoe and journal for signs of wear. Anti-friction. The advantages of anti-friction bearings are versatility, low friction operation, and ability to be packed to avoid frequent lubrication. Anti-friction bearing parts. The basic parts of anti-friction bearings are 2 hardened steel rings, the hardened balls or rollers, and the separator. A number of variations are in use. Some types, such as needle roller bearings, may be used with or without an inner ring, outer ring, or separators. If there is no inner ring, the rollers fit directly onto the hardened shaft. For specific applications, bearings may have other parts such as a snap ring used to set axial location. Figures 34 to 41 show some common bearings and bearing parts. This manual uses the names shown in Figures 34 to 38 for the parts common to all standard ball and roller bearings. L. Rolling elements. The rolling elements of anti-friction bearings are classified by 3 basic: ball bearings, roller bearings, cylindrical, tapered, spherical, needle bearings. In spherical roller bearings, the surfaces of the rollers are curved across their width and run in concave channels. Ball bushings. Ball bearings can be used as a guide for axial shaft measurement using recirculating ball bushings. See Figure 41. The balls circulate through radial grooves. Each carries only a small amount of the total load at any one time. Shields and seals. Many bearings use shields and seals to prevent unwanted material from entering the housing. The locations of the shields and seals vary. This affects the choice of bearing type. Open bearings are used where foreign material is kept out of the housing by shaft lip seals or the equivalent. The lubricant is expected to work through the bearing from one side to the other. Shielded bearings, one or both sides, are used where the bearing is exposed and the shield will keep out solids but not fluids. The lubricant is metered out of the housing into the bearing. Sealed bearings, one or both sides, are used where the bearing is exposed and the seal will keep out solids and fluids. The lubricant is to be kept in the bearing. Sealed and shielded bearings such as pillow block cartridges are used where conditions are very dirty and abrasive. When replacing a bearing with a single shield or seal, take care that the new bearing has the seal or shield in the same position as the original installation. For example, a sealed bearing on the input shaft of a small hydraulic pump is lubricated by the hydraulic fluid. The seal prevents fluid loss to the outside. If the seal is reversed, the bearing will run dry. Working conditions. Types of load. Ball bearings have a low to medium load capacity, while roller bearings usually have a low to high load capacity. Load is applied to bearings in various directions, and anti-friction bearings are classified according to load conditions. Radial load maximum, or total radial load, means that all forces on the bearing are in a radial direction, with little or no sideways thrust load. Examples are needle roller bearings and single row ball bearings. See Figure 42. Thrust load. A pure thrust axial load means there is no radial load. All forces run parallel to the shaft axis. Examples are ball and needle thrust bearings. See Figures 37 and 39 and 43. Combination thrust and radial load, also called angular load. Examples are tapered roller bearings, ball bearings with angular contact, spherical roller, self-aligning bearings. Yen. Speed. Ball bearings are generally suited to high-speed applications up to 40,000 RPM and roller bearings to low-speed applications. The speed of a bearing is expressed as either RPM or as rubbing speed. Some makes of roller bearings are good for speeds up to 20,000 RPM. The normal range of speeds is 2,000 to 20,000 RPM. Service or degree of loading. As the rated load capacity is increased, the bore stays the same but the diameter of the rolling unit and the width and thickness of the rings are increased. Service weight or service use is a means of classifying bearings with the same types of rolling element and bore for their load capacity. The service weight is shown in the code number of the bearings. Series 00100, 200, 300, 400 series. Service weight 01, 2, 3, 4 service weight. Common groups are ultra light 00 series, extra light 100 series, light 200 series, medium 300 series, and heavy duty 400 series. Other grades are also available. Bearing size and design. Dimensions and shape. Roller bearings may have either a straight or a tapered bore. Practically all bearings are made to metric dimensions. The dimensions outside diameter, OD, bore ID, and bearing width, YY, are indicated in millimeters. These are matched to the standard code markings on the bearing ring. Determining bore. The bore of a bearing is indicated by the last two digits of the bearing number. Up to 20 millimeters, the bore of a bearing is designated as 00 equals 10 millimeters, 01 equals 12 millimeters, 02 equals 15 millimeters, 03 equals 17 millimeters. Example, a 6200 ball bearing has a bore of 10 millimeters. From 20 millimeters to 480 millimeters, to find the bore, multiply the last two figures of the bearing number by 5. Example, a 6204 ball bearing has a bore of 04x5 is equal to 20 mm. Above 480 millimeters, number 6296, the bearing size is directly included in the bearing number. Example, a 62/500 or 62,500 ball bearing has a bore of 500 millimeters. Construction. Anti-friction bearings may also be classified according to their construction. Non-separable bearings are designed as a single piece. They cannot be separated easily. Examples are a single groove, radial ball bearing, or a double spherical roller bearing. See Figure 47. Separable bearings can be easily taken apart. They consist of one of the following: 3 separate parts, a housing washer, rolling assembly, and shaft washer. Examples are ball or needle thrust bearings. Dual direction thrust bearings use 2 housing washers, 2 rolling assemblies and a shaft washer. 2 separate parts. 1 separate ring with a rolling element and a separator combined with the other ring. An example is a taper roller bearing. Non-aligning bearings used in machines where the bearings are held in alignment by the bores in the housing. Self-aligning bearings may be internal or external. In an internal self-aligning bearing, the inside of the outer ring is concave. In an external self-aligning bearing, the outside of the outer ring may be convex. C. Examples of self-aligning bearings are pillow blocks for independent mounting. These are external self-aligning. Double ball or roller types for heavy-duty loading. These are internal self-aligning. Single barrel roller types for light loading. These are internal self-aligning. Self-aligning bearings can be identified by the curved surface of the outer ring, which gives a choice of positions for the balls or rollers. The degree of allowable misalignment is slight, as the balls or rollers must be in contact with the outer ring at all times. Bearing codes. This section covers the basic ISO codes for standard ball bearings and spherical roller bearings with metric dimensions. For information about the long list of prefixes, suffixes, and codes for special bearings, consult a bearing manufacturer's catalog. Tapered roller bearings have a standard code designation giving the ID of the cone and the OD of the cup. Most bearing codes give 3 pieces of information: the type of rolling element, the service weight, the bore in millimeters. Usually a sequence of letters at the beginning indicates the name of the manufacturer. Except for special cases, such as match face bearings, the orientation of the bearing code makes no difference to the service life of a bearing. However, if the code numbers face the end of the shaft, it helps the millwright to quickly identify the bearing. Basic codes for most standard ball bearings are 4-figure or 5-figure numbers following the manufacturer's identifying letters. 4-figure code. In a 4-figure code, first figure indicates the type of rolling element. Second figure indicates the service weight, outside diameter and width. This figure ranges from 0 to 4, indicating 00 series, ultralight to 400 series, heavy duty. Third and fourth figures indicate bore size. Example 1. Example 2. SKF 6208. SKF indicates the manufacturer. 6 equals Conrad. Equals single row, deep groove ball bearing. 2 equals service weight light. 08 equals 08x5 is equal to 40 mm bore. SKF 6308. The 6308 has a different OD and a different width than the 6208. 6 equals Conrad. 3 equals heavier service weight than example 1 medium. 08 equals the same bore as example 1. 5-figure code. In a 5-figure code, first figure indicates the type of rolling element. Second figure indicates OD. Third figure indicates the service weight, outside diameter and width. Fourth and fifth figures indicate bore size. Example 3. NTN 22208. NTN indicates the manufacturer. 22 equals double spherical roller, self-aligning. 2 equals service weight light. 08 equals 08x5 is equal to 40 mm bore. Compared to the 6208 bearing, the 22208 has different rolling elements indicated by 22. The same OD indicated by the third 2. The same bore indicated by 08. Different width single versus double. Example 4. NTN 23208. 2 equals rolling element. 3 equals series diameter 0. 2 equals service weight light. 08 equals 08x5 is equal to 40 mm bore. Codes for tapered bore bearings. Basic codes for tapered bore bearings are like the standard bearings but are followed by AK. Example 5. FAG 6208K. FAG indicates the manufacturer. 6 equals Conrad. 2 equals service weight light. 08 equals bore size 40 millimeters. K equals tapered bore. Note that this pillow block bearing will fit on an adapter sleeve that has a code number ending in 8 and will fit into the same bore housing. An adapter sleeve is a cone-shaped device used to locate and secure a taper bore bearing to a parallel shaft seat. Note that K designates the common 1 in 12 taper. K30 designates the 1 in 30 taper used for larger bearings. The position of the K and K30 is important. It must be at the end of the code. Other letters and numbers may appear in the bearing code. To interpret them, refer to the manufacturer's manual. For example, a shield is indicated by the letter Z at the end of the code. A rubbing seal is indicated by RS at the end of the code. 2RS indicates rubbing seals on both sides. P numbers indicate tolerances. P2 indicates close, small tolerance. P6 indicates large tolerance. Clearance. Clearance is the total internal clearance between the balls or rollers in a bearing and their raceways. This clearance has several functions. It compensates for expansion of the inner ring or for contraction of the outer ring when interference fits are used. It compensates for differential expansion of the two rings when the inner ring of the bearing operates at a higher temperature than the outer ring. It affects the end play of ball journal bearings and their capacity for carrying axial loads. The greater the clearance, the greater the capacity for supporting axial load. When using bearings with small clearances, pay select seating dimensions very carefully. Once ball and roller bearings are mounted and running, a small running clearance is usually desirable. Bearings under radial load run more quietly when this clearance is as close to zero as practicable. The definitions of internal clearance under various conditions are as follows. Initial clearance, or uninstalled clearance, is the clearance in the bearing as it comes from the box. Installed clearance is the clearance left in the bearing after installing it on a shaft and in a housing, or the clearance left in a taper bore bearing that has been forced up the taper. Running clearance is the clearance in the bearing when the machine is up to operating temperature and lubrication has been supplied. Clearances for ball bearings have been standardized by international ISO agreement. Ball bearings are made with 6 different specific ranges of clearance. ISO bearings use C clearance numbers that are usually etched onto the bearing after final inspection. Manufacturers leave unmarked those bearings that have normal, the most widely used, bearing clearance. The clearance markings are C1 through C5. C1 less than C2, these have the smallest clearance. Use them only when freedom from all vibration is required and when there is no possibility of their clearance being eliminated by external causes. C2 less than normal, these are used where a normal bearing would allow too much deflection in the shaft. NO mark, this is the standard clearance, normal. C3 more than normal, these are used where running temperature of a normal bearing would eliminate all the clearance. C4 more than C3, these are used where there are press fits on both rings, housing and shaft. CS more than C4, these are used for the same job conditions as C4 bearings when there will be a marked rise in temperature. P numbers. P numbers give further subdivisions of the C clearance markings. They classify the bearing's tolerance. P numbers range from P2, close tolerance, to P6, large tolerance. Installing and removing. Anti-friction bearings, colon, 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 dot, colon, comma, dot, colon, dot, colon, 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 colon. Bearings are installed, fitted, square on the shaft. They are installed in several ways. To determine appropriate fitting methods, the housing and shaft must be checked. Bearings may have a push fit or an interference fit. Shaft and housing checks. Before installing any bearing, check the shaft and housing for diameter, roundness out of round, a shaft deflection, bending, any surface damage that will cause high spots on the bearing seat, general finish, any damage to the shoulders supporting the inner ring, cracks in the housing. Be careful when using an emery cloth to improve the shaft surface. Do not remove the interference that is deliberately built into the shaft diameter. Checking the shaft, wipe it clean and coat it with light oil. With a press fit, you may need to use an anti-seize compound. If the housing is split, check the corners for damage and correct them if necessary. Push fit. Push fit means that a bearing is installed by hand without mechanical aids. This method may be used whenever the bearing can be held in place by mechanical aids such as snap rings. Creep. Creep is the very slow rotation of a push-fit bearing race. One rotation of the ring by creep requires several million revolutions of the rest of the bearing. Creep changes the contact area on the raceway and extends the life of the bearing. Interference fit. Interference fit is a description of how tightly a bearing fits on the shaft. Interference is expressed as a measurement. The amount of interference in the shaft and bearing ring is exactly equal to the clearance reduction in the bearings after installation. The purpose of the interference fit is to hold the bearing ring firmly in position and reduce the clearance to a specified amount. To achieve an interference fit, bearings are installed using press or shrink fits or by using a taper adapter sleeve. In a press fit, a mechanical means of applying force is used. Shrink fits use expansion and contraction of metal during temperature changes to firmly position the bearing. Examples of fit and clearance. For information on shaft and bearing dimensions, see shaft and housing fits to ISO standards. Fits and clearances are available in most bearing manufacturers' catalogs. In general, for any parallel bore bearing, the tighter the bearing is on the shaft, the less clearance is left in the bearing. The usual bearing installation has one ring with an interference fit and another ring with a push fit. In mounting a straight bore bearing, the rotating ring is a press fit and the non-rotating ring is a push fit. Some installations, for example, a separable bearing, use a press fit on both rings. Most bearing applications that millwrights deal with require an interference fit between the shaft and bearing inner ring. Press fits press ram. Press fits are used with small bore bearings. To press fit a bearing, you use a tube to distribute the force. Evenly. A bearing can be pressed onto the shaft, or the shaft pressed through the bearing, depending on the shaft, design and weight, and on the components in place on the shaft. For example, when replacing bearings in a 3-shaft reduction unit, the bearings are usually pressed onto the intermediate and final shafts, but it may be easier to press the input shaft through its bearing. Figure 50, previous page, illustrates a typical design of tube or press for pressing a bearing onto a shaft. The press ram bears down on a tube, which is in contact with the bearing's inner ring. With large diameter bearings, a plate is needed between the ram and the tube to distribute the press force evenly. Use eye protection when press fitting bearings. To press a bearing onto a shaft. 1. Apply a coating of light oil to the bearing bore and to the shaft to reduce friction. 2. Put the bearing on the shaft, making sure that it is square to the shaft. 3. Place a clean pipe or mounting tube slightly larger than the shaft diameter on the inner ring of the bearing. 4. Apply pressure by hand to start the bearing moving into position. 5. Check the position of the bearing to see that it is still squarely on. 6. Press it to the final position. 7. As the bearing moves down the shaft, rotate the outer ring by hand to check for drag or loss of clearance. If the bearing clearance is lost partway down the shaft, do not press the bearing the rest of the way. To press a shaft into a bearing. When using an arbor or hydraulic press, do the following. 1. Use a groove or slot in the press bed that just clears the shaft. The support blocks must be flat, smooth, and of the same thickness. 2. Make sure that the support blocks touch both the inner and outer rings of the bearing as shown in Figure 51. Shrink fits. In a shrink fit, the dimensions of a bearing are changed before assembly. This simplifies the initial bearing to shaft or bearing to housing assembly by allowing the parts to slide together. The fit tightens as the temperatures of the parts equalize. The dimensions can be changed in 2 ways in each type of assembly. In a bearing to shaft assembly, heat the bearing or chill the shaft. In a bearing to housing assembly, chill the bearing or heat the housing, chilling the bearing. To shrink fit a bearing, chill the bearing or the shaft in a mixture of dry ice and alcohol or in liquid air. These methods are preferred because they are easier than heating the housing. Dry ice and alcohol has a temperature of -79 OC, LLUF. Liquid air boils at -190 OC, -310 of. Take extreme care to avoid frostbite when freezing a bearing or shaft. Use approved protective equipment. Heating the bearing. The recommended maximum temperature for heating a bearing varies from manufacturer to manufacturer. Heating beyond the maximum temperature may soften the bearing metal. The bearing is usually heated 45 to 50 degrees Celsius, 80 to 90 degrees Fahrenheit, above the ambient temperature. Above 120 OC, 250 of the bearing. Structure changes may be permanent. When heating a bearing, always stay close enough to check the position and temperature of the bearing throughout the process. Do not exceed L20 degrees C, 250 degrees Fahrenheit. When heating the bearing, the heat source must be clean, gradual, and indirect. Various heat sources are used. Heat lamps or infrared lamps can be used for small bearings. This is a slow process, but has the advantage of allowing the bearing to be heated either wrapped or unwrapped. An oven can be set up to heat bearings. This is a relatively safe way of heating a bearing, as the temperature can be controlled. Before using the oven, check the heat settings with an accurate thermometer. A good induction heater is quick and quiet. Early induction heaters or one-stage heaters left residual magnetism in the bearing. This attracted any ferrous particles in the oil lubrication system. Modem two-cycle induction heaters have a demagnetizing cycle to produce a non-magnetic bearing. This method has no visible way to control heat, so expansion must be checked by marking the outer ring using a wax crayon called temp stick or other material which changes state at a known temperature, or measuring the bore of the bearing to check for the required expansion. An oil bath is used to heat large bearings using an oil with a high flash point. To do this, keep the bearings out of contact with the bottom of the pot, as it is important to keep the bearings away from any localized heat source. Use wire handles as shown in Figure 53. Keep the temperature below 121 OC, 250 degrees Fahrenheit. During the heating, check the ID of the bearing against the OD of a shaft using telescopic gauges or other comparator tools and a micrometer. There should be sufficient expansion for a slip fit. To do this, 1. Measure the shaft with an outside micrometer. 2. Set the telescopic gauge to the outside micrometer setting plus the necessary expansion. 3. Use the telescopic gauge as a standard to check the bearing. Once the gauge can slip through the bearing ID, the oil level bearing is ready for installation. Figure 53 Oil Bath. Installing a hot bearing. When installing a hot bearing on a shaft, move it quickly to its final position to keep it from seizing. If any resistance is felt, remove it as quickly as possible and reheat it. Press or shrink fitting stretches the inner ring of the bearing and reduces the internal clearance. If too tight a press or shrink fit is used, the bearing's internal clearance will be eliminated or reduced so much that the bearing will drag and seize when it warms up. See the section on interferon. Clearance. A replacement bearing such as a tapered roller or an angular contact has the end float controlled by shims. When these bearings have cooled, check them for a possible gap between the shaft shoulder and the cone or inner ring, see Figure 55. It may be necessary to press the bearing ring tight against the shoulder. Installing bearing outer rings. An outer ring can be installed in either a board, one-piece, solid, housing or a split housing. Split housing. To install bearings in a split housing. 1. Install the bearings on the shaft. 2. Put the mechanical assembly into the split housing. 3. Install the caps. 4. Torque the bolts. Board housing. A push-fit bearing must be started square with the housing. If the ring is misaligned at the start, the ring will not self-align as it is forced into the bore. Axial positioning. If radial load bearings are installed with a minimum of interference, it is easy to assemble and remove them. A press or shrink fit is suitable for holding a bearing in position on the shaft, but positive keeping, that is, using a device to hold the bearing in place, may also be needed. The device may give a definite position to the inner ring, the outer ring, or the cap. The bearing may have a straight bore on a straight shaft, or it may have a tapered bore on a tapered shaft. The threaded portion is straight or parallel, positive position of the inner race. Bearings may be held by the snap ring holding the bearing in place is in a groove cut in the shaft or housing. A large washer having the same diameter as the inner ring is flush with or slightly protrudes over the end of the shaft. The bearing, lock nut, and washer have a straight fit on the shaft, a tapered fit in the bearing. Positive position of the outer race. In tapered roller bearings, the inner ring is called the cone and the outer ring is called a cup. The end caps of the bearings are used for positive positioning, axial, with or without shims. For small bearings, the snap ring is in the housing. Bearing, snap ring, for positive positioning of outer ring. Floating and fixed bearings. To prevent end float, only one bearing on any shaft assembly should be fixed axially in the housing. This is called the held, or fixed bearing. It is generally better to hold the bearing at the drive end. All other bearings on the shaft should have axial clearance in the housing to allow movement. They are called free or floating bearings. This allows the shaft to expand and contract. Plant policy and the availability of space for rings determine whether fixing is done with 1 or 2 stabilizing rings. Either assembly method holds the bearing in position as shown in Figure 62A. The floating bearing is usually in the center of the pillow block, never on the shoulder. If the installation uses a relatively long shaft and the shaft is subject to a marked heat rise when in operation, a better position for the floating bearing is shown in Figure 62B. Fixed/floating assemblies do not include axial control bearings, such as tapered roller, and angular contact bearings. Axial clearance, or thrust adjustment. Tapered roller and angular contact ball bearings are mounted so that the end float of a shaft between 2 bearings is held to a required minimum. Thrust adjustment may be made in 2 ways. Adjust the inner race or cone when the outer race or cup is fixed in the housing. Adjust the outer race or cup when the inner race or cone is fixed on the shaft. In most industrial applications, the outer race is adjusted by means of an end cover and shims. The amount of clearance to be obtained is determined by the manufacturer's specifications for the machine. Figure 63 shows 2 places where shims can be used to achieve end adjustment. At point A, the ring shims are between the bearing cup and the end cover. Adding shims decreases axial clearance. Removing shims increases axial clearance. At point B, the shims are between the end cover and the machine housing. Adding shims increases axial clearance. Removing shims decreases axial clearance. P. Figure 64 using shims to adjust end float. Thrust control can also be obtained by using a single taper roller bearing or a single angular contact bearing on one end of the shaft and allowing the other end to float. Arrangement of angular contact bearings. These bearings are bought and installed as a matched pair, matched duplex. There are 3 basic arrangements: back-to-back, face-to-face, tandem. The arrangement selected depends on the load, speed, direction, and amount of thrust, and which ring is the press or push fit on the shaft or in the housing. See Figures 65 to 67. Back-to-back arrangements are used when the outer ring is push fit. Figure 65 shows a back-to-back matched pair. Notice that the outer rings are tied up to each other in the housing, but there is a gap between the inner rings on the shaft. When the lock nut on the shaft is tightened, the inner ring closes up, leaving no gap. The movement puts a definite amount of preload into the bearing set. Note that this amount of preload is not adjustable. Face-to-face arrangements are used when the inner ring is push-fit. Figure 66 shows a face-to-face matched pair. In this case, the inner rings touch and the outer rings have a gap. When the bearing end cap or cover plate is tightened, the gap closes, and this preloads the bearing set. Tandem arrangements are used when both rings are press-fit. The inner or the outer ring is ground down a given amount by the manufacturer. Figure 67 shows a tandem pair. They are also called face-to-hack matched pairs. In this arrangement, the back surfaces of the outer rings are supported against the housing shoulder. They carry thrust in one direction only. This provides maximum thrust capacity for unidirectional, axial loads applied along the shaft. Installing taper bore bearings. Using sleeve adapters. The use of a tapered adapter sleeve allows you to mount a bearing at any place on a standard shaft. The sleeve has the following characteristics. The outer face of the sleeve is tapered to match the tapered bore of the bearing's inner ring. The sleeve is slotted to permit expansion and contraction. The sleeve is threaded at the small end to take a lock nut. When the sleeve is drawn up tight, a press fit is made with both the shaft and the inner ring. When adapter mountings are used, take care that the bearing is not tight internally, or clearance will be eliminated. Mounting ball bearings using a tapered sleeve adapter. To mount ball bearings, the general procedure is to 1. Rotate the outer race and swivel it slowly while tightening the lock nut. 2. You will feel a light drag on the bearing when the clearance is reduced. 3. At this point, stop tightening and lock the nut in position with the tab. Washer. Mounting taper bore bearings using a hydraulic nut. When mounting taper bore bearings using a hydraulic nut. 1. Check the reduction in radial clearance of the bearing to ensure proper installed clearance exists. 2. Dismounting the bearing hydraulically gives an abrupt release. Make sure a stop, such as the shaft or sleeve nut, is provided to act as a stop during dismounting. Mounting spherical roller bearings. Check the clearance. 1. Check the initial clearance by inserting a feeler gauge between the top rollers and the outer ring as shown in Figure 68 on the next page. 2. Press the two top rollers inward to assure their contact with the center guide flange, as well as the inner ring raceway. 3. Check the clearance by starting with the thinnest feeler, preferably 0.0015 inch, using progressively heavier blades until one fails to go through. The blade thickness before not go is a measure of the clearance before installation. Mount the bearings. 1. Apply light oil, or other suitable lubricant, to the outside, and to the threads of the tapered sleeve, and to the threads and face of the lock nut. 2. Assemble the parts, locate their position on the shaft, and check for initial clearance. 3. If unloaded rollers are at the bottom, make sure they are raised to the seat on the inner race and set against the guide flange. 4. Assemble small bearings with the tab washer in position. Mount large bearings for final clearance with the tab washer left out. Then install the washer and tighten and lock the nut. This prevents the forces involved from shearing off the inside tab of the washer. 5. Tighten the adapter nut with a spanner wrench until it is snug. The adapter sleeve may have a tendency to turn, but it can be held in position until it binds on the shaft. 6. Drive against the nut, using a hammer and soft steel bar to release the pressure on the threads. 7. Tighten the nut with a wrench, then check for clearance. 8. Repeat this driving and tightening until the final clearance is reached. 9. Secure the locking tab washer. Reduce the clearance. You must reduce the amount of initial clearance to suit manufacturer's recommendations. Example 6. Initial clearance equals 0.004 inch. Recommended reduction equals 0.0015 to 0.0025 inch. Average reduction equals 0.002. Final clearance equals 0.002 inch. Example 7. Initial clearance equals 0.007 inch. Recommended reduction equals 0.0026. 0.0025 inch. Average reduction equals 0.003. Rounded off. Final clearance equals 0.004. A reduction of 0.0026 inch would leave an installed clearance of 0.007 inch. 0.0026 equals 0.0044. This would be suitable where the load is uniformly from one direction, or when the shaft heats during operation, but the housing stays cool. A reduction of 0.0032 inch would leave an installed clearance of 0.0038, 0.007, 0.0032 equals 0.0038. This would be suitable where the temperature of the shaft and housing remains relatively even, but the bearing is subject to a reciprocating load. Therefore, 0.004 inch is an adequate estimate of final clearance. Any bearing installation involving high temperature changes or heavy reciprocating loads should be installed according to specifications. For standard clearance, spherical roller bearings only, when no tables are available, a rule of thumb is to reduce the initial clearance by roughly 50%. Another rule of thumb is to convert the last two figures of the bearing number into thousandths of an inch, for example, 2224-0.0024 inch. Reduce the initial clearance by this amount to get installed clearance. Bearing removal. Non-destructive removal. The best way to pull off a bearing with the minimum amount of damage to the bearing shaft is with a set of pullers or a press. When using a press, make sure that all the strain is applied to the inner race and the strain is even on the opposite sides. The parallel bars are under the inner race. You can use a bearing splitter and a two-jaw puller to remove a cone from a shaft. See Figure 70, next page. With this setup, make sure that the jaws of the puller do not bear on the threaded section of the rods holding the puller. In some installations, it is not possible to pull or press on the inner ring. Force must be applied to the outer ring only. This increases the binding action of the inner ring on the shaft. It can also fracture the outer ring. When pulling or pressing on the outer ring, wrap or guard the outer ring to prevent injury from flying fragments in case the outer ring breaks. This wrapping is important when using a hydraulic power source. Cup puller. You can remove bearing cups from a housing with a cup puller, also called an inside puller, provided that the jaws can be inserted behind the shoulder. See Figure 71. After the bearing is removed, future problems can be prevented by drilling and tapping for 2 set screws in the bearing cap. During operation, these tapped holes can be filled with hollow head set screws. Withdrawal and adapter sleeves. When the outer ring is mounted in a solid housing, a withdrawal sleeve. When the outer ring is mounted in a solid housing, a withdrawal sleeve assembly may be used with a standard tapered bore bearing to permit easy removal of the sleeve and bearing. The differences between a withdrawal sleeve and an adapter sleeve are as follows. Withdrawal sleeve. Solid board housing. Shaft is machined as needed. Sleeve slides under the bearing. Driving nut is threaded onto the shaft. Bearing is held by a shaft shoulder or a machined part against the inner ring. Installation procedure. The bearing first, then the sleeve. Adapter sleeve. Split board housing. No shaft changes. Bearing slides over the sleeve. Driving nut is threaded onto the sleeve. Bearing does not need a backing or shoulder. Installation procedure. The sleeve first, then the bearing. Both styles of mounting use the same routines to check the initial clearance and reduce the required installation clearance. Removal of bearings mounted with adapter sleeves. Method 1. L. Pry the tab washer tab out of the slot in the lock nut. 2. Remove the lock nut and washer. 3. Drive or pull the bearing off the wedge on the sleeve. Use force only on the inner ring. See Figure 73, Method 1. 4. Remove the sleeve and the bearing from the shaft. Method 2. 1. Pry the tab washer tab out of the slot in the lock nut. 2. Back the lock nut to the end of the sleeve. 3. Use a tubular drift against the lock nut to drive the sleeve through the bearing. See Figure 73, Method 2. 4. When the bearing is loose, unscrew the lock nut and remove it. Also remove the lock washer, the sleeve and the bearing. All parts may be used again after they are thoroughly cleaned and examined. Destructive removal of a bearing. Destructive removal is used for bearings on a shaft when the bearings are definitely not to be reused. An oxyacetylene torch is used to cut away the bearing rings. The procedure is as follows. 1. Cut through the outer ring in 2 places 180 degrees apart. 2. Cut away the roller assembly in 2 places 180 degrees apart. 3. Carefully cut away the inner ring as follows. A. Hold the torch along the surface of the ring. B. Move the torch slowly back and forth across the surface to wash away the metal of the bearing ring. C. Stop just before you break through the metal. D. Tap lightly with a hammer if necessary to break away the ring. E. Pull the ring off. Welding a bead. Bearing cups are frequently set in seats with no room to use a set of pullers. In such a case, the cup can be removed by welding a bead on the face of the raceway. This will shrink the bearing diameter. Hydraulic oil injection removal. Hydraulic dismounting removal uses the force developed by oil or grease under pressure to expand the inner ring of the bearing. Figure 77 shows a shaft modified for oil injection by cutting a semicircular groove at the approximate center of the bearing and drilling a supply line to a fitting at the end of the shaft. The oil injected into the shaft and groove is under pressure. It expands the inner ring of the bearing, making it easy to remove. Oil injection equipment can be either of the following. A grease gun capable of developing over 1,000 psi. A hand-operated pump for a portable jack, using SAE 40 or heavier oil. Hydraulic dismounting of taper bore bearings. To hydraulically dismount bearings mounted on a tapered journal, oil is pumped between the contact surfaces of the sleeve and shaft. This immediately and abruptly releases the press fit. Make sure a stop such as a shaft nut is in place. Pillow block installation and removal. Pillow blocks are housings used to independently mount anti-friction bearings. They come in 2 main groups, split and one piece. Split housings. The most common bearing housing has a base and a cap separated by a horizontal split. See Figure 78. The housing sections are put together so that their mate marks match. If there are no mate marks on a housing, make your own before disassembling the housing. Horizontally split. A horizontally split housing has the following 5 components with code numbers. If they are standard, their last figures are the same. The housing A 2-bolt, 4-bolt, or plain case with no drilled holes. The bearing self-aligning style. Adapter style 10D to suit the stock bearing, 2 more possible ID to suit shaft diameters. Tab washer. Bearing nut. The assembly also has seals, blanking discs, and locking or fixing rings for a held assembly. Vertically split. A vertically split bearing housing has a one-piece ring and a base with separate end covers. One-piece housings. Pillow blocks with one-piece housings are pre-assembled. The unit can be slipped over a smooth shaft and bolted into position. Unlike a standard bearing, the inner ring is extra long to distribute the load over the shaft. Common designs are single groove ball bearings for high radial, low axial thrust capacity, double taper roller bearings for high radial and axial thrust loading, spherical or concave rollers for high radial and axial thrust loading. These bearings are externally self-aligning because of the shape of the outer ring, which rocks or pivots in the housing. This self-alignment allows more misalignment than a self-aligning split bearing. Refer back to Figure 48. The inner ring is held in position on the shaft in various ways depending on the manufacturer. Two common methods used are: thread 2 set screws into a collar and pass them through matching holes in the inner ring to engage the shaft. Use a self-locking collar, camlock, held in place by 1 or 2 set screws. This is only used on unidirectional drives because it is eccentric. Mounting. A pillow block is mounted with its base parallel to the shaft. When mounting, installing pillow blocks with one-piece housings, tighten them on the base before locking the inner ring in position on the shaft. This allows the bearing to align to the shaft. Removal. When the bearing must be frequently removed, file a flat spot on the shaft at the set screw location. For easy removal of one-piece bearings, mount them with the screws or set screws on the side away from the shaft end. If the shaft is damaged by the set screws, you will not need to move the bearing very far to clear the rough surface, and there will be less contact between the bearing's long inner ring and any roughness on the shaft. Mounting other bearings. Flange bearings. A flange bearing has its base at 90 degrees to the shaft. See Figure 79. Flange bearings are available in 2-, 3-, and 4-bolt styles. The inner ring, rolling element, and outer ring of flange bearings are supplied as a unit called a cartridge. To replace a cartridge: 1. Pivot the worn bearing at the loading notches. 2. Pull out the cartridge. 3. Slide in the new cartridge. 4. Pivot the new cartridge to the correct position. Needle bearings. One common type of needle bearing has no separators or inner ring, but only an outer ring and the rolling elements. To keep the needles in place before mounting, the bearing is fitted with a temporary sleeve or inner ring of shaft size. During mounting, the bearing, with its sleeve, is pushed over the shaft so that the shaft pushes the sleeve out. See Figure 80 and also Figure 38. It is possible to coat smaller needle bearings with light grease so that they stay in position during mounting. Thrust bearings. Thrust bearings, Figure 81, are designed to carry thrust axial loads. Because of centrifugal force, these bearings are limited in the speed at which they can be used. A dual-direction thrust bearing has 2 housing washers and 1 shaft washer. Single and double thrust bearings are mounted in the same way. To mount thrust bearings, fit one ring to the housing and the other to the shaft. Maintaining anti-friction bearings. Keeping bearings clean. If bearings are in good condition, dip them in oil or grease before installing them. If they are not, clean them. Do not wash bearings with seals on both sides. Wipe them off with a clean rag to keep the dirt from working inside. Treat bearings with one side shielded like bearings without a shield. Cleaning bearings without shields. To clean a bearing without shields, do the following. 1. Use recommended solvents in a well-ventilated area. 2. Soak the bearing in the solvent long enough to loosen the grease and dirt. 3. Rotate the races slowly to work out the old lubricant. 4. When using an air hose, don't spin the bearing. Hold both races and let the air jet blow out the particles. 5. Finish washing the bearing in a container with clean solvent. The use of solvents creates a fire hazard. Do not use firefighting equipment to hold solvents. Some commercial solvents remove all traces of lubricant from bearing surfaces. This leaves a dry bearing with metal-to-metal contact. This may give a false reading when checking bearing wear. Storing bearings. Cover the clean bearings with a light coat of oil. Wrap the bearings in a special, acid-free bearing wrapper, oil-impregnated paper, and store them in a clean, dry place until needed. Partial assemblies should also be cleaned and covered until needed. Attach a tag or label to the wrapping with the bearing code number and the machine for which it is used. Preventing bearing contamination. Avoid bearing contamination by keeping surrounding things clean as follows. 1. Work in clean surroundings on a smooth bench. 2. Use clean tools in good repair. 3. Handle bearings with clean hands. 4. Remove all outside dirt from the housing before exposing bearings. 5. Lay bearings out on clean paper. 6. Wipe bearings with clean, lint-free rags. Seals. Seals are used to keep the lubricant in the bearing housing and contamination out. They may be mounted on the machine or as part of the housing. Various types of seals used for anti-friction bearings are shown in Figure 82. Lip contact seals. Lip contact seals come in two forms. Commercial seals. These seals have a contact lip of synthetic rubber or leather with a spring backing for more positive sealing action. They are used where a shaft is totally or partially immersed in oil. Felt seals. These seals are good with grease at low speeds. They are not suitable for high speed, high temperature, or abrasive conditions. Annulus seals. Annulus seals are a series of grooves in the housing or end cover with a drain hole at the bottom. These are non-contact seals. There is a very slight clearance between the rotating and stationary parts. They are not effective if the drain plugs. Labyrinth and flinger seals. Labyrinth and flinger seals depend on centrifugal force to throw material away from the housing. Annulus and flinger seals. Annulus and flinger seals keep oil in and foreign material out. For more details, see Chapter 14, Seals. Keeping bearings in good condition. To keep bearings in good condition, you must continually check them for wear and other signs of failure. All bearings need regular lubrication with the correct lubricant. Check for bearing wear. Check as follows. 1. Be sure that the bearing is flat or horizontal. This ensures that there is contact all around the ring. 2. Hold one ring stationary and turn the other ring slowly. 3. Turn the bearing over and repeat. 4. If the bearing is self-aligning, double ball or double spherical, misalign it and check all around the outer ring. Check for bearing failure. Continually check for the following symptoms of bearing failure. Temperature rise. Increased vibration. Unusual noise. The most common cause of anti-friction bearing failure is contamination. Dirt or foreign material gets into the bearing during assembly or works past the seals during operation. Lubrication. You must use the grade of grease or oil recommended for the particular bearing and its application. For a double row of self-aligning bearings. 1. Misalign the outer race and pack grease between the balls or rollers. 2. If the bearings is in position in the bottom half of the pillow box, force the grease through the openings on one side. Do this until grease shows. On the other side. Continued. 3. Fill the case 1/3 to 1/2 full of grease. 4. Oil lubrication. Fill the case to a point halfway up the lower ball or roller. 4. Deep groove ball and cylindrical roller bearings. Pack the grease well between the balls or rollers, covering both sides of the bearing. Maintaining Cooper, split, bearings. Most anti-friction bearings are considered to be one-piece units. However, where installation and removal of bearings is not practical because of other components mounted on the shaft, the Cooper bearing may be used. It is a split bearing with all its components and has as shown in Figure 85. To maintain these bearings, you must pay attention to the whole assembly. Separate it and then maintain each part. Special cautions. Problems in adapter sleeves. The inner ring may be forced too far up on the taper. This expands the inner ring enough to bring the clearance reduction below standard. Check the clearance with feelers and back the bearing off if clearance has been reduced too much. If the inner ring is not tight enough on the sleeve, allowing the ring to tum on the sleeve or the sleeve to tum on the shaft or both. During installation, the sleeve needs to be free to tum on the shaft and the inner ring of the bearing needs to tum on the sleeve. The tab washer is not set on the lock nut, allowing the nut to back off. The sleeve and ring may not be free to tum. See the next page for some special working precautions. Always cover an exposed bearing after working on it. Also, do not mount radial bearings or self-aligning roller bearings with heavy thrust loading. Do not mount angular contact ball bearings backwards. This causes heavy thrust on the shallow shoulder. Do not use too few or too many shims when mounting thrust bearings and casting. Always use the correct clearance for end play. Do not mount self-aligning bearings at too extreme an angle. They are self-aligning to a small degree, but should be mounted as evenly and as level as possible. Do not hold more than one bearing on the shaft. Allow room for expansion. These actions may cause overloading and failure of the assembly.